A log structured tree or an LSM tree optimizes for fast writes. Unlike its counterpart, B plus trees, LSM trees append new data to the end of data which already exists on disk. It believes in immutable data structures and does not update data in place. In this video, we'll be focusing on designing a scalable and an efficient compaction engine for an LSM tree. Now, we'll start off by discussing what actually is an LSM tree, how does it work, then come up to what is the reason for compaction and what compaction actually is, strategies for compaction, and then design the compaction engine by the make and break model which we follow. First of all, every storage design follows the Rum conjecture and is designed by simplifying the model. That is, there's a rule of thumb known as the Rum triangle where it offers us three overheads: read, write, and memory. So, out of these three, we can only optimize for two, and often read and memory overhead walk hand in hand, and we have to either choose from write or read and space. LSM trees go for writes most of the times, and when it tries to optimize for read and memory, writes are lost from hands. So let's look how LSM trees actually achieve fast writes. LSM tree, which follow the idea of never updating in place, actually use two types of structures. There are SS tables on disk, which are sorted string tables, and store keys in sorted fashion on disk. These are immutable. Unlike mem table, which are stored on RAM, these are also sorted but mutable. Now, we can mutate a single key with its newer value on RAM. Why? Because it is very cheaper compared to writing on disk. So, for example, version 0 has a key X called 123, and we just flush it on the disk in the form of a SS table. Now, when we update X with a newer value again, we don't update this SS table in its place. Rather than that, we just append another SS table on disk. This is the newer version. Now, this is how, using an append only model, the writes become fast. But obviously, the read and space will be compromised because now there are different versions of the same key in different SS tables. Some are old and some are even deleted. And we will have to fetch the correct or the latest key during the read time. This is achieved by merging the SS tables together into a new SS table which has the latest value. Now, this is all done during the read time. Therefore, the reads are very slow compared to writes, and we compromise on reads. And as there are redundant keys in many of the SS tables, the space is also amplified, and so we have space debt as well. So, optimizing for writes gave us read and space debt as gift. So we follow something known as compaction. That is, rather than merging only during the reads, we choose some trigger points like a time period to merge these SS tables regularly. So the SS table A and B, which have x is equal to 10 and x is equal to 30, are merged together to give us the new SS table where there is the latest value of x which is equal to 30 and the older and redundant value of x is dropped. Now, read and space amplification here are managed. But as the merge runs very frequently, the write amplification increases again. So the triangle is doing its work. So, how do we strategize for these merges? We cannot actually strategize in a very good manner. Rather, we will have to look for the strategies for certain work scenarios for which we will optimize. These strategies work on something known as layers or tiers. That is, we pick the SS tables from the lower tiers, merge them, and replace the SS tables of lower tiers with the merged big SS table. Now, we'll have to take care of the discarded SS tables and remove them or delete them from the disk or memory, but there's a complication in that which we will see further in the video. Now, there is the size tiered compaction strategy. What happens in this? Now, several runs or several SS tables of similar sizes exist in the same layer. And when several SS tables are there, that means if it reaches n, that is a threshold number of SS tables, they're merged together into a bigger SS table on the higher layer. Now, we write only when it reaches a certain number of SS tables. That means every byte is rewritten few times. So we have low write amplification here. But there's a drawback. Because of this, in the same level, for example, if we merge this layer and produce a bigger SS set, and now we have different SS tables here in this layer, and this needs to be merged again. So the newer layer will give us something which will have SS tables with the same keys in many files. Now, as we have to access different files for retrieving the same key, we again encounter read and space amplification. So that's the rule of the thumb, that if the bytes are rewritten fewer times, we will have lower write amplification. But if we have the key ranges overlapping, we will have higher read and space amplification. So that's how it works. So we can use this size tiered compaction strategy where we require cheaper writes, that is in write heavy workload, for example, Cassandra. Now, there's something known as leveled compaction strategy where we have different levels. In level 0, which is written directly from the mem table, we have overlapping key ranges. But in the further levels, we do not have these overlapping key ranges. We tidy them up and make sure that different SS tables in the higher layer do not have overlapping key ranges. Now, because of this, we have higher write amplification because we will have to tidy the higher layers again and again, and the lower layers will have overlapping key ranges. So that is why the write amplification is there. But as the higher levels do not have overlapping key ranges, the read amplification and the space amplification is much lower because there are non-overlapping key ranges. So we can just go into level 1 or level 2 and check the SS table which has our desired key. Now, how do we build the engine actually? We discussed what is compaction and why it is needed, but how do we actually build it? So this is the very naive approach that we are writing, and the writer thread encounters a trigger which needs to compact, and then we block on a multi-GB run before the writer thread returns to the user. Now, what happens here? Here the latency obviously spikes on every compaction or every flush, and the throughput collapses by a lot. So a simple solution is that we do not keep compaction on the right path. The right path should not be handling compaction. Rather than that, compaction should be living in background. So what happens here? Whenever the writer thread encounters a trigger for compaction, it allocates a worker in background to do the compaction. So several workers in background are now responsible for handling this compaction. And so the writer thread returns fast, unlike we saw before. But how do we actually decide that which worker compacts what? Because there are several SS tables which need to be compacted. We cannot compact all the SS tables of level 1 to level 2 and level 3 to level 5 at the same time, we need to be decisive about which compaction needs to take place first. So, for that, like an operating system, we design a scheduler, and a, s- and a scheduler is a priority job queue for which we can use a simple message queue like RabbitMQ, or can even model Kafka to be used as an MQ. But here in this video, we are just generalizing it and modeling it as a simple MQ. So we score the candidates based on some factors like size target in size tiered compaction strategy, and if there are threshold number of files in level 0, if certain number of keys are overlapping, and if there are certain number of tombstones. So we take these factors, derive a formula, and then score the candidates, and then put them in our priority queue, which is our message queue. And the highest priority of workers are then dequeued from this and are enqueued to a worker pool. And now this worker pool handles our compaction. But now every worker and every reader needs to know about the metadata of the LSM tree, of the structure. So we generally have a metadata file which tells us about the location of SS tables, which tells us about the condition of the mem table. So there's one metadata file which we also call a version file. So every reader and every worker is accessing this metadata. So how do we guarantee the concurrency? We can say that we can guard this metadata using one mutex. But now the problem of serialization comes, which we don't want. We don't want every read to be blocked. That's very bad. So guarding the live file with metadata will defeat our whole purpose of actually introducing the background worker pool, because now nothing is parallel. This mutex serializes everything, and a reader has to go after other reader. A worker can lock, a reader can lock, and everything becomes serialized. So we can follow a lock free idea. Now, how do we do this? Now, this live metadata file, which is known as a version, can be an immutable snapshot. That is, it should not be editable, and rather, the older version can be replaced with the newer version. That means the readers can access a version file almost concurrently. And compaction does not edit this version, it actually produces the newer one and it replaces the older one with the newer one. Now, why the mutex was wrong? We discussed that the mutex serializes everything. If the compaction workers block the file, the version file, every reader is blocked. And only after the compaction releases the lock, a reader can run. So, reads are very common and they should never wait on a background merging. So, rather than locking, we follow the idea, we derive the idea from this thing that compaction actually should not edit the version, rather, it produces a new snapshot. And we use compare and swap. That means we atomically compare the newer version with the older version and swap with the newer version file using compare and swap. You can read on compare and swap and how it is implemented, but the detailed implementation of CAS is not in the scope of this video. So now, as a new version is produced, the pointer can be swapped atomically using the compare and swap strategy. And readers can just check on this pointer and see which version is live now. But there's a problem. We cannot just discard version n after the current pointer points to the newer version. What if some readers are still accessing version n. So yeah, this is the bug which I talked about. Now that version n is gone and reader which was mid scan of version n is actually scanning version n plus 1, but we already deleted version n. Now what do we do? If we read the read file, it will cause a corruption. So what do? We actually strategize upon when should we delete. So there are two strategies which we can use. First is reference counting. When a reader is accessing a version file, the reference count is incremented, and when the reader is done, the reference count is decremented. Now when the count of the version hits 0, then it is safe to delete that version file. And the other is epoch based. Now what's an epoch? Epoch is a monotonic timestamp, which is not the wall clock but just an incrementing period timestamp. So what happens? There's a global epoch counter. For example, the whole version has the global epoch 7, and readers which access it see, okay, the global epoch is 7, I am in epoch 7. Now the newer version which comes increments the global epoch count 8. Now before deleting the older version, we see if there are anything which are lesser than global epoch count 8. So if some readers are still in epoch count 7, we don't delete it. Now if readers access the newer one, which is epoch count 8, and there are no readers left which access the epoch count 7 version, so now the version file, the older version file, can be deleted. So these three things can be done, that an immutable version can be made, an atomic swap which follows compare and swap strategy, and reference counting or epoch based, some of the things which we can choose. And this is the heart of our compaction engine. Now let's discuss about the sad path actually, where compaction can't keep up with the rate of ingestion. That means as an LSM tree, the write rate is obviously high, and level 0 piles up, read amplification climbs. How does it happen? Because there are overlapping keys. And then as read amplification climbs, it triggers a compaction, but compaction is not able to keep up with the ingest rate. What do we do now? We apply the policy of back pressure. That means that writers don't come as often. That means it's just a glorified name of rate limiting. So we have two limits, soft limit and a hard limit. Yes, we will have to be defensive here if our compaction takes down the whole engine. So we will have to soft limit it first. That means we will throttle our writers. So we'll tell them, okay, don't come as frequently. Please be throttled. Come one after the other nicely. And if it hits the hard limit, that is our last resolve, we will stall the writers and tell, please stop. And when compaction catches up with the ingestion, then we will say, okay, please go on like the way you were going on. So we will have to choose the back pressure configurations very carefully. Now, there are several complications in how to choose the jitter rate, retry rate, everything in back pressure. And that's a whole different topic to study about. Now, we can also hybridize our engine to use both the strategies which we discussed above. Now, the upper layers, which are very write heavy in the leveled tier, because level 0 receives writes directly from the mem table. So, as they are write heavy, we can make them size tiered. Why? Because we discussed above how size tiered is supported and very efficient for write heavy data, and the lower ones which hold cold data and aren't written to very often are read optimized so they can stay as leveled. And we can follow such hybrid model, which is that RocksDB does something like LO to L1 is sized and the below are just leveled, and Scala also does this thing. Now, a few more concepts actually construct the heart of LSM trees, which we'll see very briefly, not in much detail. So let me close this toolbar. Okay. Okay. Yeah. So Bloom filter. Now there are overlapping key ranges. So we don't want to check all the SS tables to check if the key is present in this SS table or not. We want to have some candidates. So what do? We take a key, we use several functions and hash this. Then we get some results out of those hash functions. So if there are three hash functions, we get 1, 4, and 7, and we set 1, 4, and 7th bit. And this tells us that, okay, these are present in these SS tables, but some other key, for example, if we set some bits using key 1 and key 2, which set these 4 bits, and key 3 gives us this, and this bit. So it will tell that yes, key 3 is also present in these SS tables, and that is a false positive. So a Bloom filter gives us false positive, that is, this key might be present. But if it is not present, it is definite that okay, it's definitely not present. So we can skip the candidates which are unpromising, and we can go over which are like the key might be present. So it filters out the candidates for us. Second is fence pointers, or a data structure known as skip lists. So for example, if we are looking for a key 100, and in a file there are these keys 140, 80, and then we binary search and we get key number 80, and then we jump from this file's key 80 to another file's 80, and we move from 80 to 90, then from 90 we jump to another file's 90, and we go from 90 to 100 and get the key. And as these are sorted, we can use these files and make a skip list data structure. This can be studied more comprehensively. This is just covering how we optimize our engine more and more. Tombstones, I think tombstones we have covered enough. That is, whenever we have to delete, we don't effectively delete, we just mark it as a tombstone. That is okay, don't consider this data, this is deleted. So when we delete x from level 0, we just mark that okay, this is not there, and level 2 x is there. So whenever this is merged, this is reconciled, and the key x is dropped altogether. Now there is something known as manifest. Manifest is nothing, it's just a write ahead log, that before writing into the memory, we actually write the order of operations in a file known as manifest. So that is, we added file 18 to level 0, then removed these files and added this file to level 1. What does this do? For example, the version or the in-memory metadata which lives in memory can be lost on stoppage of the program. So we want to recover it, and we can recover it by replaying this manifest from start to finish. Now, this manifest also has several complexities or several things to do with. So we can see that in some another video or a separate blog. And now this is our complete compaction engine. Let me zoom out a bit. Yeah. So let's go over it once again. Okay. So writes. First, it goes through the mem table, and then it flushes to the disk. Now, this disk has something known as a version or a metadata file, which is a snapshot of live SS tables. And we always uh, replace the older with newer using something known as compare and swap so that it is lock free for readers and workers to access. Where do workers come from? We do not want to make the compaction engine on the right path, so we make it in background threads. So we have a scheduler which scores our candidate, puts them in the priority queue. The priority queue dequeues the highest priority jobs, puts them in the worker pool, and the workers go one by one, access this version again, and then do the compaction in background. And we use back pressure. Why? Because we don't want compaction to be lagging behind ingestion, and these are the supporting actors. So compaction is the price which we pay for the fast writes of LSM tree. And that's it for this video. So we looked at how we can design a good compaction engine using different system design primitives. That's it. Yeah, see you in another one. Bye.